MES College Marampally e-learning.
Hi everyone, I am Anju Sara Varghese, Assistant Professor, Department of Physics, MES College Marampally. Welcome to my session on determination of magnetic field of a solenoid using Ampere Circuital law. This topic is mainly focusing on the students of 5th semester BSc Physics under the course Electricity and Electrodynamics. Let us start with Ampere Circuital law. Ampere Circuital law is one of the most important laws in magnetostatics. This is similar to Gauss's law in electrostatics, and it was first discovered by Anne-Marie Ampere in 1826. Ampere Circuital law is an alternative way in which the Biot-Savart's law can be expressed. Both the laws relate the magnetic field to the current and both express physical consequences of electric currents. The purpose of the law is to find the value of magnetic field at a location from a current carrying conductor if the magnetic field is symmetrical. In order to apply Ampere's law, all currents have to be steady, that is, current do not change with time. Only currents crossing the area inside the path are taken into account and have some contribution to the magnetic field. Now let us see the definition and explanation for Ampere Circuital law. The law states that the line integral of magnetic field over a closed loop is mu0 times the current enclosed by the loop. It can be mathematically represented as closed integral B dot dl is equal to mu0 into I enclosed, where I enclosed is the net current enclosed by the loop and mu0 is the permeability of free space. The value of mu0 is given by 4 pi into 10 raised to minus 7 Newton per ampere square. Here, the line integral does not depend on the shape of the path or the position of the conductor with the magnetic field. Next is solenoid. As we all know, a solenoid is a long coil of wire closely wound in the form of helix as shown in figure. When an electric current is passed through the solenoid, definitely a magnetic field is produced. The total magnetic field of a solenoid is due to the superposition of magnetic fields of each turn of the solenoid. Inside the solenoid, the magnetic field is nearly uniform and parallel to its axis. It is due to the fact that when the magnetic field lines is moving from first turn of the solenoid to the second turn, it will not get enough time to diverge since the turns are very close to each other. But outside the solenoid, the field is negligibly small. Based on the behavior of current, one end of the solenoid behaves like north pole and the other end behaves like south pole. Then, how to find magnetic field at a point inside the solenoid? For that, consider a solenoid of length L and having number of turns N. The diameter is assumed to be much smaller when compared to its length and the coil is wound very closely. To calculate the magnetic field at any point inside the solenoid, we can apply Ampere Circuital law. For that, consider a rectangular loop A, B, C and D as shown in figure. Then from Ampere Circuital law, we have closed integral B dot dl is equal to mu0 into I enclosed, that is mu0 into total current enclosed by Amperian loop. Then the left hand side of the above equation is closed integral C B dot dl is equal to integral A to B B dot dl plus integral B to C B dot dl plus integral C to D B dot dl plus integral D to A B dot dl, since we are using a rectangular loop A, B, C, D. Since the elemental lengths along B, C and D, A are perpendicular to the magnetic field, which is along the axis of the solenoid, the integral B to C B dot dl is equal to integral B to C B dl cos 90 degree, which is equal to 0. Similarly, integral D to A B dot dl also equal to 0. Since the magnetic field outside the solenoid is 0, we have integral C to D B dot dl, which is also equal to 0. So the only remaining path is A to B inside the solenoid, such that integral A to B B dot dl is equal to B into integral A to B dl cos 0. Since B is a constant, we can take B outside the integration, and finally we get B into integral A to B dl, where the length A to B is given as h in figure. But the choice of length of loop is arbitrary. We can take a very large loop such that it is equal to the length of the solenoid capital L. Therefore, the integral is integral A to B B dot dl is equal to B into L. Now, Ni be the current passing through the solenoid of n turns, then our equation will be integral A to B B dot dl is equal to BL, which is equal to right hand side of Ampere's circuital equation, that is mu 0 into n into I. Equating these two equations, we will get B is equal to mu 0 into n into I divided by L. Now the number of turns per unit length is denoted as small n, which is equal to capital N by capital L. Then B is equal to mu 0 into n into I. This is the equation for magnetic field at a point inside the solenoid. To conclude, we have the equation for a magnetic field at a point inside the solenoid is B is equal to mu 0 into n into I. Here the values of mu 0 and n are constants. So for a given solenoid, for a fixed current I passing through it, the magnetic field inside the solenoid is also a constant. Hope all of you got basic ideas of Ampere's circuital law and its application in solenoid. Thank you.